All right. So in section 5, we kind of add a little bit more to our knowledge of thermodynamics. Okay. So we bring to this process what we call a spontaneous process. Up to this point, we've talked about delta H, or change of enthalpy, which at constant pressure, which is what we do in this class here, or the conditions we have, enthalpy or change of enthalpy is simply just the heat change. However, we have not talked about if our reaction is spontaneous or not, okay? And so what section 5 does is it looks at, is a reaction spontaneous? So the first thing we'll talk about here is, what is spontaneous? Well, it's when we have a physical or chemical change that occurs without outside intervention. What that means is that no help is needed to either start the reaction or complete the reaction here. So 2 examples here, both takes different speeds, which we'll get to in the next couple of chapters on kinetics. But right now, iron rusting and the combustion of methane, let's lighten those methane gas bubbles on fire. Both of those things have a negative delta H, and they occur spontaneously. But a negative delta H does not necessarily guarantee that we are going to have a spontaneous process here, okay? And so if we take a look here about the sign with delta H and something occurring spontaneously, we see iron rusting and methane, the previous 2 examples, both of those things are negative, okay? And that means that, remember, your heat is released, or it's an exothermic reaction. But think about ice melting, okay? Ice melting at room temperature is normal. It's going to happen, right? You put an ice cube out, it's going to melt into a puddle of water. And so I want to make a note here where it says, down here under 2C, it says a process was first thought to be non-spontaneous always. And then underneath that here, it says all endothermic reactions are non-spontaneous. This right here, I want to highlight, and I want to say this, okay? This statement that I'm highlighting was later to be proved false, okay? So this right here, I just want to make everybody clear, is false. Just because something is endo or exothermic doesn't necessarily guarantee that it is spontaneous, okay? So let's dive a little bit more in depth and in detail here with entropy, okay? So entropy is defined as a measure of the possible ways that energy of a system can be distributed, and is related to the freedom of the system particles to move and the number of ways they can be arranged. Okay, that's a big fancy definition. What I want you to concentrate on is this. Entropy is measure of disorder. Okay, so I always talk about trying to keep your room clean. No matter what you do, it's naturally going to get dirty with clothes thrown everywhere, things like that all over the room. You have to put effort to make your room clean. Same thing that occurs in a chemical process here, okay? The more disorder you have, the more chaos you have, means the more particles are going every which way and at higher speeds and higher temperatures, okay? So now we have this idea of entropy, and we can enter into the second law of thermodynamics. So the second law of thermodynamics states that a spontaneous process always proceeds in a way in which the entropy of the universe increases. Again, second law of thermodynamics. So this is saying, hey, in a chemical process that is spontaneous, more particles are going to spread out in more regions, and there's going to be more disorder, okay? Now, we can keep going through this, and we can look at this. Our change in entropy is something that we can also calculate as we go through this particular process. Now, this should look really familiar. I've said over and over again, products minus reactants, products minus reactants. Well, you can take the entropy of your products, subtract it from your reactants, and you can get the entropy of your entire system, okay? And so I want to talk about a couple of things. Number one, just like enthalpy, it's very hard to say, hey, this has this much particular energy at this point in time, but we can measure before and after points here with our products and our reactants. So what does an increase in delta S mean? A delta S, that's positive, an increase means that more entropy is occurring, so more disorder. A decrease is a negative delta S, and that means there now is more order, right? So let's put this even more into perspective here. We want to predict the sign of delta S. And we don't even have to tie fancy numbers to it. We can. I don't do it here in this particular class, but I want to tie a couple of things to this, okay? Number one, if we took at vaporizing water and melting of really any substance, vaporizing and melting here. Check this out. Both of these things have a delta S that is greater than 0, meaning there is more disorder, there is more entropy, okay? So I want to point out a couple of things. Check this out. Liquid to a gas. Liquid, those particles pretty close together. Gas, particles are really spread out, right? So there's more chaos, there's more disorder. So I like to think of it like this. Imagine trying to babysit 2 kids and they're contained in a relatively small space, let's say a room. Well, now they get the entire house to roam. There's going to be a lot more disorder and chaos because they can get into a lot more things around that house, okay? Same thing with a solid to a liquid. Solid particles locked really tight in places. Not much movement. Remember, a little bit of movement, not much. Liquid, now we have more room to roam. So again, states of matter. Solid to a liquid, increase. Liquid to a gas, also increase. Now let's go the reverse process here. Okay, so now let's talk about gas. And this is great if you're thinking about soda. Soda, remember, is carbonated. And so gas that is now going into this aqueous solution of, let's say, soda, is now trapped in that particular liquid, okay? Gas, particles really far apart. Now they're in that aqueous solution, the liquid portion there, and your delta S is less than 0. Now, what we call this is more order has occurred, okay? More order has occurred. Gas, particles really far apart, liquid, particles close together. So again, back to my babysitting example, okay? You had the kids all over the house, and now you say, hey, you have to be in this specific room. Again, a lot more control, a lot more order can happen with those kids babysitting or you babysitting them in one particular room. All right, so now we go through this part here. And this part is a little bit challenging at first. We'll work through some more practice here. But check this out. In our example problem here, all of our particular states of matter are gases. Okay, so I can't use the gas example or the changes of states of matter because all of these things are a gas. I want you to check out this. We can look at our total number of moles. So on our left-hand side, there are 2 total moles of a gas. Moles of a gas. Okay, and I should probably put mole of our gas. On the right-hand side, check this out. There's 2 moles from SO2, and then there's an additional mole from O2. So on the right-hand side, there is 3 moles, or I should say 3 total moles of a gas. Because there's more moles of gas on the right or the product side, your entropy increases. Again, more chaos. Now, if the roles are reversed, entropy decreases, okay? And we'll get more and more practice with that and recognizing, hey, states of matter and total number of moles of gas, how can it be either positive or negative? Again, we get down here and we check out, hey, solid, remember, aqueous, I don't like to associate it with liquid, but we can associate it with liquid. So you had 1 part of sodium chloride, and now you have 2 parts. Again, there's more chaos. There's more parts to worry about. Your entropy or your disorder is increasing. It's positive, okay? And we'll go over more and more practice here. And so remember, all of this stuff can be tied back to the kinetic molecular theory, which we talked about in our states of matter chapter. And what we can do is this. Our last thing is talking about the temperature. So let's say we don't have a change or a chemical reaction or a change of state, but guess what? Now our temperature increases. Well, guess what's happening? Particles are moving faster. So again, back to my babysitting example, you hype the kids up all on sugar. Now they have a ton of energy. There is a lot more disorder. Same thing happens here with temperature. A lot more energy occurs in a substance that's hotter. And so as a result, your entropy increases, or it's above 0, greater than 0. Again, we will look more and more at this, okay? Now we get down to how we can predict whether something is spontaneous or not, okay? So we kind of started this section and we said, we can talk about heat change, but that does not correlate. And I pointed out some false parts on the notes there. That does not directly correlate to knowing if a system is spontaneous, okay? So we need a way that we can look at entropy and we can look at enthalpy. We can't forget about that and say, okay, under certain conditions, is this spontaneous or not? And so what we get is this, all right? We get some unique things here, and I'm going to go to the next slide. We get Mr. Gibbs, that's the scientist in this picture here. He said, hey, I'm going to talk about free energy, and I'm going to end this and say, hey, free energy is the energy available to do work, meaning does a reaction happen spontaneous? So he does a very fancy equation where he ties your delta H, your enthalpy, with our delta S, our entropy. And he ties it into this formula here, delta G equals delta H minus T delta S, okay? Now, we tie in temperature, and for this formula, our temperature has to be in Kelvin, okay? That's an important point. So let's try an example here and determine if something is spontaneous or non-spontaneous. And I want to point out before we go to the next slide, positive delta G equals non-spontaneous, negative delta G equals spontaneous. Negative spontaneous, positive non-spontaneous. Okay, so if we look at this, we can actually predict using Gibbs free energy formula, whether it's spontaneous or not. Okay, so we're going to go through 4 scenarios. The first thing that I'm going to identify up here at the top is I'm going to say delta G is equal to delta H minus T delta S. And my first condition here is this. I'm going to say that my delta H in case number 1 is positive, and my delta S is also positive, okay? So both of these things are positive, okay? A positive delta H minus a positive delta S. Well, no matter what, in this scenario here, because delta S is positive, your number will continue to get smaller and smaller and smaller. Your delta G will continue to get smaller and smaller and smaller, but you have to have really, really high temperatures. So I'm going to put this as whether this is spontaneous or not. These conditions, positive and positive, it can be spontaneous at high temperatures. And I'm talking very high temperatures. Like 700 Kelvin would be a very good example. Okay, so that's pretty hot there. Then case 2, let's make both things negative. Okay, so let's call our delta H in this case, let's say it is negative. And in this case here, we'll call delta S negative. So if we look on our formula here, we have a negative delta H minus T times a negative delta S. Well, no matter what we do on the right-hand side, we're going to have minus a minus. So no matter what, that delta G is going to continue to get bigger and bigger and bigger. Okay? That means we have to have a delta H to be very negative to go through this particular process. Okay? We can have a spontaneous condition occur. I'm going to say this can be spontaneous, but only at really low temperatures, right? We want to stay negative to make delta G negative, and this is spontaneous at really low temperatures. And I'm talking close to 0 Kelvin, all right? Now, let's try some other things here. Let's say delta H is positive, and let's say a condition in which delta S is negative. Again, if we just think about this into our formula, delta H positive minus a minus thing from the negative delta S. No matter what, delta G will be positive because a positive delta H and a negative delta S is always positive. This set of conditions would make this a non-spontaneous process at all temperatures. And then let's talk about our last case here, okay? Let's talk about our last case. And that's where we're going to have a negative delta H and a positive delta S. Okay, now under this circumstances, no matter what we do, delta G will always be negative, which means that this is going to be spontaneous at all temperatures. All right. Let me correct one thing here. Just want to make the colors match. All right, so again, if you're not following what I'm doing here, all I'm doing is plugging hypothetical numbers back into my delta G formula. And with these hypothetical numbers, I can predict if something's going to be spontaneous or non-spontaneous. And if it is going to be spontaneous, what conditions or what temperatures does it need to be at? Okay. We'll revisit this and we'll go over it a little bit more when we tie in this next set of information, okay? So let's go through this, all right? Gibbs free energy. For the most part, it's a pretty standard formula, okay? The one thing we have to be careful on it is units, okay? So in this process here, down in our example, it says for a process, a delta H is equal to 145 kilojoules and a delta S is equal to 322 joules per Kelvin. We want to know, is this process spontaneous at 382 Kelvin? Okay, so our delta G, again, I like to break these things down into their individual components. Our delta G is unknown, and that's going to help us determine if a process is spontaneous or not. Our delta H is simply 145 kilojoules. Our delta S is 322 joules per Kelvin. And here's where our first issue comes into play. Delta H is in kilojoules, delta S is in joules. We have to convert these. Now, it doesn't matter how you convert it, because at the end of the day, we just need to look at delta G and determine if it's positive or negative. I'm right here at delta S, so I'm going to go ahead and convert this. And remember, there are 1,000 joules in 1 kilojoule. So if we took 322 divided by 1,000, this would end up as 0.322 kilojoules per K for Kelvin. And then our temperature here, I'm going to put that down below. Our T for temperature is 382 Kelvin, okay? So let's go ahead, let's plug this back into our equation and see what we get. So we get delta G equals our delta H, which is 145 kilojoules, minus our T, and I'm going to put a parenthesis right here, our T, which is 382 Kelvin, times our converted delta S, 0.322 kilojoules per Kelvin. And I'm going to close my parenthesis and go through this, okay? So how I have this typed in is exactly how you need to type it in on your calculator. So we need to take 145 minus parenthesis 382 times 0.322, close the parenthesis. I press enter, and I get a value. Actually, I have to round here. I get a value of 22.0, okay? So my delta H, delta G is a positive 22.0 kilojoules. This positive sign, or your sign, is the most important part of this process. A positive delta G is a non-spontaneous process. Okay, positive, non-spontaneous, negative, spontaneous. It's very important to keep in mind here. All right, let's try one more example here, and then we'll end section 5 here with a couple other side notes. Okay, so now this one here gives us our delta H, our delta S, and our T for temperature. Okay, in this scenario here, because I already gave you our values, I just want to do one thing. I want to remind you of the formula. Delta G equals delta H minus T delta S. And then I want to go ahead. I like converting my delta S to kilojoules. And so what I'm going to do with this is I'm going to take our delta S, which is negative. Very important to remember here. are negative 197 joules per Kelvin. And I'm going to say times on bottom 1,000 joules, on top 1 kilojoule. And that gets us a value of negative 0.197 kilojoules per mole. Okay, so now let's go ahead and let's plug all that back into our equation. Okay, so we're trying to find Gibbs free energy. So we don't know here our delta G. So we don't know delta G out in front. We do know our delta H is at negative 91.8. Negative 91.8 kilojoules minus our T, which our T, remember, T delta S. I'm going to start with a parenthesis. Our T for temperature is 298 Kelvin. 298 K for Kelvin times our value of kilojoules per mole we just converted of 0.197 kilojoules per mole. Okay, now we are going to, in that parenthesis, and we're going to type this value in exactly how we see it. Okay, so into our calculators, we are going to take negative 91.8 minus parenthesis 298 times negative 0.197, close the parenthesis, press enter, and we get a value. I'm going to go to 1 decimal. Our delta G value is negative 33.1 kilojoules. Now, the most important part out of this, that negative sign, that represents a spontaneous process. Okay, so we can use Gibbs free energy, determine whether it's positive or negative. Negative is a spontaneous reaction. Positive is a non-spontaneous reaction, to quickly determine, hey, is this process a spontaneous or a non-spontaneous reaction? Okay. All right, so let's end our section 5 notes here with this. All right. Why is this important? Okay. Well, having this free energy, if you've taken a biology course, I'm sure the biology teacher has said, hey, remember, there is this free energy in this type of process. All right. So this is dealing with your energy in your body. Obviously, you can see the ATPs and the ADPs, that cellular process that produces energy that we can use as living creatures. Okay. And that is really important to know, because that info uses spontaneous and non-spontaneous reactions to produce the correct amount of energy, or produce that energy very effectively. Okay. So remember, spontaneous cannot be determined directly from your enthalpy or heat change. We have to add in entropy, which is the measure of disorder, and we can put those things together in Gibbs free energy, which is delta G for Gibbs equals delta H minus T delta S. And a positive delta G is a non-spontaneous process, and a negative delta G is a spontaneous process. Okay.